Why is it that Venus is a hotter planet than Mercury? I don't know that it is, but if it is, maybe because it's bigger. The smaller you are, the more you're gonna cool off. Venus is very similar to our size, Earth. I'm like that annoying kid. No, it's all good. This is all good. Mercury is very small, so I don't know. I don't know if its temperature is less than Venus is, but I could see that being the case because Venus is larger. So, like for example, Jupiter is a lot of mass, right? So Jupiter is so big. Jupiter is significantly farther away from the sun than us or Venus or Mercury, right? But Jupiter has not cooled down to be rock or anything like that. It's a gas giant. And that's because it's so big. The mass of it doesn't allow it to, the big mass of it does not allow it to cool down enough to become like rock or anything solid. It continues to be a gas giant. The seed of ignorance is born, thou shalt not think, thou shalt conform. What is that? Did you Google that? I think pretty much it's something like that. That's what I was trying to get from the book. But basically, if it puffs up to become a red giant, then we have bigger problems at that point already. So that's what I was trying to get at. Basically. Hi Scorpion. So it turns out depending on there are these lower mass stars like cousins of our sun, but depending on exactly what mass, you might even have certain other types of processes, like convection might be different. So the evolution of more massive stars on the main sequence is similar to that of their lower mass cousins, with one important difference: the existence of a convective core. The convection zone continually mixes the material. So by the way, this is very important. Depending on if you're doing convection in your core or not, you're going to have a different mixing up of things in the star, obviously, right? So depending on, so it sounds like there are some more massive stars on the main sequence who have this important difference from their lower mass cousins, which is the existence of a convective core. The convection zone continually mixes the material, keeping the core composition nearly homogeneous. This is because the time scale for convection, defined by the amount of time it takes a convective element to travel one mixing length, is much shorter than the nuclear time scale. For a 5 solar mass star, the central convection zone decreases somewhat in mass during core hydrogen burning, leaving behind a slight composition gradient. Moving up the main sequence, as the star evolves, the convection zone in the core retreats more rapidly with increasing stellar mass, disappearing entirely before the hydrogen is exhausted for those stars with masses greater than about 10 solar masses. With the mass fraction of hydrogen, when the mass fraction of hydrogen reaches about 0.05, in the core of a 5 solar mass star, the entire star begins to contract. With the release of some gravitational potential energy, the luminosity increases slightly. Since the radius decreases, the effective temperature must also increase. For stars with masses greater than 1.2 solar masses, this stage of overall contraction is defined to be the end of the main sequence phase of evolution. Wow. So depending on Okay, I think we're getting close to where we need to be in this discussion. Oh, yes, thank God. Oh, thank you, God. The giant, I think I just had to keep going in that same chapter. We're going to talk about the giant now.